The future is watching. Welcome to OpCode Virtual Summit.
Let's see how it works actually. So can you see my screen? Yeah, so this is about just using Intel PT for general vulnerability analysis or exploit analysis, or maybe possibly security researches in general. So I work for Darren Green. It's a new company, just one-person company right now. So maybe I can introduce because many people doesn't know me, I think. Actually, I'm the author of Darren Green Patch Dipping Tools maybe 10 years ago. So after I joined Microsoft 10 years ago as a security researcher, actually, there were some legal bindings that I can't work on the open source project at the time. Now it's very loose, but at the time it was a very strict because it was the previous CEO, and he hated open source, right? But now I'm out of Microsoft and I'm just trying to revive the framework as a more data science kit that you can work. Right? You can use Jupyter notebooks to load binary data, and maybe you can perform some statistical analysis. It's still work in progress. And as I said, I worked for Microsoft for 10 years, and I worked as a defender, but now I look into both sides. The NSO groups you talked about, all these groups, the 0 days, whenever the 0 day comes out, then MSRC and our team actually work together to find how the exploit mechanisms, how they are bypassing, those things, to research those things. So currently I'm just startup starter. So it's really early phase. I'm just looking around different technologies and how I can use them for possibly security product or maybe threat analysis, right? So Intel PT is one of those technologies. So what is Intel PT? So it's a processor trace actually, right? So the feature is supported by the processor from the hardware. And the documentation actually says it is supported from Broadwell, actually, Intel Broadwell CPUs, but practically it only works after Skylake CPUs. And all those tools and anything that are available, they only work on Skylake. But most Skylake, I don't know, it was 2017, I guess. I don't know exact timeline when Skylake was available. It was 4 or 5 years ago. So most of your computers might have these features embedded already. So what you can do with Intel PT? So basically you can trace code execution in instruction level. Technically, they only trace control flow changes, but combining with the instruction images, actually you can reconstruct full instructions. So you can use triggering or filtering by CPLs. Maybe you can just trace kernel code executions, or maybe you can just trace process images. CR3, maybe if it accesses some memory pages, maybe then you can access it, right? Or you can filter by IP ranges. Maybe you want to just monitor some code executions inside some modules, for example, right? Those things are possible. So it's very strong. And if you know how to use this technology, it will help you very well with multiple different jobs in security field, actually. So it's not just for example, the AFL fudging, right? So they are trying to use, they made the AFL fudger using Intel PT as a kind of feedback loop for the code coverage, right? But it's very slow. So you will know why it's very slow. I don't know if there is any improvement these days, but last time I checked, it was very slow. So the intended usage is actually post-mortem analysis of crashes or some performance issues. You want to actually collect these traces, and you can check where all the CPUs are used for code executions, and you can just fix it, right? And when some program crashes, actually you can enrich the code stack information using this Intel PT. So this presentation is not actually, I don't want to go really deep into the Intel PT. I will just go overview of this technology. But with this presentation, we want to explore the practical, right? So practical, again, not about writing papers or those things, academia researches, but more of how we can really use it for daily basis jobs, right? So that is the focus of this talk. So using Intel PT on Windows, I spent a lot of time just figuring this out, actually. So because originally the Windows Intel PT tool, it was released by the Cisco Talos guys, actually, right? So one of those guys is actually working for Microsoft now. He made this tool. Actually, it does every single small configuration for Intel PT, actually, right? So it's from scratch. It's a driver, but it only works for Windows 10 pre-RS6 because after Windows 10 RS6, Microsoft introduced IPT.sys. As the name suggests, actually, it's the driver for IPT collection, right? So this driver actually checks whether there is another session actually going on. And if it detects Windows Intel PT or any kernel driver that actually accesses some specific MSR area, then it will actually blue screen the system. So you can't use Windows Intel PT for Windows 10 post RS6. But conveniently, Alexei Ionescu actually made this WinIPT tool that is wraps around this interface for IPT.sys, and you can just conveniently use that. So it's really easy. So the other option is actually using Intel debug extension. It's a Win debugger extension, right? So you have you need actually two machines, two physical machines. One machine you actually launch Win debugger with this extension installed, and the other machine is the target machine with kernel debugging enabled and USB kernel debugging enabled, and you need special USB cable for those work. It's, I don't know, $16 or $20 somewhere, Newegg or maybe Amazon, they sell it. And you connect it actually using the remote kernel debugging session. Actually, you can initiate these Intel PT sessions. So for Linux, there are a lot of information. Actually, you can just go to this link and you can find a lot of good information. Actually, the real challenge comes when you try to decode this Intel PT log, actually, right? So for analysis of this recorded package, actually, you can use libipt library. It's a multi-platform library from Intel. It is basically a very standard library that can expand this Intel PT traces into human readable, maybe instructions or dump code. So mainly you will use two tools, ptdump and ptext. ptdump is just dumping the raw data from the binary trace log. It's not like exe, ptxed actually. Xed is the disassembler from Intel. So ptxed is actually disassemble actual instructions from Intel PT trace log. So for this decoding purposes, actually, because the Intel PT only logs control flow changes, so it only logs the actual addresses, bunch of addresses using different packets. So it doesn't save actual instruction bytes. So you need to have that instruction sources somewhere. From this diagram, for example, ptxed uses ptdump, the trace log, as a source for the control flow change. And PE or ELF files as a kind of raw instruction byte sources, right? And you can take the actual raw instruction bytes from process dump. The only problem is that PTXED doesn't understand P or process dump. It understands ERF, I guess. But, usually I do some researches on Windows platform. PTXED doesn't understand P. The only way is based upon this PT dump. It shows them some address informations, right? So extracting that address informations from these executables or process dumps, you need to manually extract those instruction bytes because it's a raw instruction byte without any headers, nothing, just raw instruction bytes. PTXD takes some inputs as those files, raw instruction byte files, and they can reconstruct free instruction based upon that. So for practical purposes, just you will just spend whole day just figuring out which memory area you want to take out for this PTXD tool. So I don't think you can use it for any practical purposes. So maybe you can just investigate whether the process dump, the PT dump is correct, or it has some information you might want, right? So there is another challenge is like because Intel PT relies on these static instruction bytes. For example, if you think about G code execution, so just think about Edge or Chrome browser, they use a lot of memory area, right? They just run JavaScript code as a assembly code, just compile and run, and the area is garbage collected. It will be gone. Then there is no point, you know, whether the memory area is actually the instructions that actually the Intel PT logged or not. So that is one challenge. The other challenge is shellcode. Shellcode actually very similar to JIT actually, but it's just static code, right? It's not compiled, but it just lives on the memory and goes away. So these two of them are challenges and possibly limitations with Intel PT technology, but yeah, somebody will figure it out how we can do that. But for now, we just want to focus on some static memory images and how we can figure out how we can just analyze some control flow changes we are interested in. To understand or use Intel PT actually, so because Intel PT is uses a lot of compressed recording, actually you want to understand how they are compressing these records, and it will help you very well with further analysis because it will give you a lot of hints about those control flow changes. So one barrier in utilizing Intel PT is just compressed format. And you need to decompress. You need to use libIPT, I said. For example, there is a branches, right? So similar to LBR. So I don't know if you are old school, you remember LBR. So somebody actually from the reverse engineer community, someone actually tried to use LBR to reconstruct a full code coverage, I remember. But Intel PT is more powerful actually. So when CPU encounters any branch instructions, jump, JE, call, read, any instructions that makes these branches, right? Then it will record the actions. And it uses T or NT 1-bit information for these jumps and no jumps, actually, right? It just recorded in very, very compressed format. I will talk about those packages later. So indirect calls and jumps, so there's no way you can just use a very small compressor format. You just record the full thing. Sometimes it just compress it. Maybe if it is 64-bit address space, maybe you can just record 32-bit based upon whether it's a near jump or far jump. Right? So unconditional branches, just like a jumps or maybe calls to some static predetermined memory addresses, then actually you don't need to record it because from the instruction bytes, you can figure it out, right? Those things are just gone. Intel PT logs will not have that information. And this will make a lot of confusions actually when you try to understand the Intel PT logs. So IP compression itself, whenever it logs some instruction pointer logs, actually upper parts are missed whenever some overlap happens with some previous records, actually. So to save those space. So to record all these things, they use package, right? Package are just package. And there are a lot of different packages, but PSB is some kind of boundaries, because if you log a lot of information, maybe some data in the middle may be corrupted. I don't know, maybe sometimes hardware error or something, but you don't want to throw away whole thing. Right? PSB just make it packet boundaries. So any information inside that boundary, they're just valid as itself. You can just take them, and they will make sense itself. Right? So that is PSB. Actually, through this presentation, we will call it sync offset, right? PSB locations, we will refer it as sync offset because libIPT code actually use sync offset pointing to PSB locations. So it's very convenient just using sync offset as this term for PSB locations. TIP is target IP. Whenever you call something for indirect jumps, indirect calls, you need to log whole thing, right? So in that case, it's a TIP, target IP. TNT is whatever you take jumps or not taking jumps. So compression overview. So based upon this PSB, TIP, TNT, TIP, TNT, it just repeats. And based upon this data, actually you can reconstruct full instructions. So if you look at some trace logs, actually, here's a snippet of IPT logs. Actually, I can share a full thing later. But if you look at this, this is output from, actually the original PT dump is binary, right? So using PT dump, you can make it as text format so that we can understand what is happening. Of that 1C, it has a PSB. It has a lot of pad bytes, but it means that from here, actually, we can make sense of these IPT logs. Add offset 3 dB, for example, for this log. It says tip PGE. So there is a PG packet. It means the instruction pointer is located at the location indicated by the packet, which is 0007. Yeah, it's a very familiar address space, right? So 3470. So we are starting from there. So this packet is logging something starting from here. So this location, right, from this packet tip PGE is here. So I extracted this from IDA. You can extract it from process dump too. So you can see that all these instructions are just doing some stack operations, maybe GS60, maybe shellcode, I don't know. Then it just goes and calls some static address. And it has TPGE indicated from this location. The next call is very interesting, right? Because this call is just a static location inside the binary. So from the packet, it doesn't log anything about this call. So the execution actually will continue to the target address of this call. And if you use PTXCD, it will actually decode everything here. So it doesn't know it doesn't care about the boundaries of these calls or anything. It just follows these instructions. So for indirect calls, somehow you can just decode the full thing. There is no instruction that are interesting, but here 63332 location equals some RAX location. If you are just human, you can just figure out, oh, RAX is coming from here. So you can just know that, oh, this is the location, right? But whatever these tools, they need some information, control flow change information. And it just logs the lower bytes. So it's for FB70. FB70, it's calling there. CS location. I don't know, there is some address discrepancies here, but address is 3332. Yeah, maybe this is for other one. So 33 TIP just designated some indirect codes, and you know that the target is 4FB70. And decoding continues, 70 just goes, and now you have J and G, so it's branches, and you need to figure out it took the branch or not. That is coded as TNT. So dot dot, I figured out this is not taking it didn't take two conditional jumps. Actually, this is typo. I have some typos here. But next, it will encounter read instructions at FE94. Then we might know from this just statically analyzing this assembly, we know that where it will return, but this thing doesn't know where it will return. So the process trace will record the location of the return address, right? Return address is basically indirect jump. So decoding continues and so on, right? So this thing is this is how it works actually. So actually I can show you. Yeah, I can share later actually. So the only challenge we have, some challenges we have is that if you decode full instruction bytes for example, if you run Office program, for example, 10 seconds, it will generate 1.4 or 1.5, for example, right? For 1.4, 1.5 size of process trace, for example, because it just dumps the ring buffer, full ring buffer memory that is designated from the command. Then out of those, the actual the recording is only, I don't know, few hundred megabytes. But if you try to expand full instructions out of it, it will become, I don't know, actually I couldn't expand everything for just 10 seconds of Office trace because the output is too big for every single instructions. Possibly it will be a few hundred gigabytes. And if you use libIPT tool, actually I couldn't finish it because when I run it on my machine, I have a server machine at home. I waited, I don't know, 16 hours to decode a 10-second amount of IPT log because I wanted some full logs for the process space because you don't know whenever some exploit works, you never know where the actual exploit will jump to. And I wanted that full logs, right? So just a few hundred megabytes of actual Intel PT data expanded to a few hundred gigabytes, possibly data, and just decoding takes possibly more than a day. So it's not really practical. So I figured out the decoding process is very slow because libIPT just uses single CPU because it's just simple operation. So you are supposed to build your tools upon this libIPT because it's just library. So IPT analyzer is just Python wrapper around libIPT. I just exposed very, very essential methods out from libIPTs. I just built my own class out of these libIPT functions, and I just exposed some of those methods. Maybe you can expand it later for your purposes. But basically what it does is just doing the operations we did, the decoding operations in parallel. This is possible because all these packet boundaries are kind of independent. So if you run multiple processes using this libIPT or IPT analyzer code upon this separate PSB boundaries, right? Packet boundaries, then you can actually process them separately, then reconstruct them later as a one single code execution path. So that is the idea, and it took a few days just to build the tool. Basically, I can show you the code. Basically, what it does is just exposing very simple interface, right? Just open the libIPT, you get the sync offset, and you can add image base, because when you want to decode some instruction byte, the IP locations, you actually need that actual instruction byte images. So you can add it, and you can actually decode some instructions at some point. You can actually decode it by block segment or something. And actually you can get some information from the IPT file too. The actual interface, Python interface, is in PyIPT. So this is the wrapper, right? So it has one instruction class. The first is just IPT, some general class. The next one is instructions, blocks, and error codes, right? So it's just three simple classes, right? You want to work on some blocks. Block means page blocks, right? Blocks or instructions from IPT log. So you can open some IPT log using IPT class. You can locate some code blocks you are interested in, and actually you can dump actual instructions from those blocks. So that is the idea that I had. So based upon this interface wrapped around the Python, you can actually build different tools. And these are some example tools that I built. For example, you want to enumerate every function calls from these IPT logs. Using libIPT, it's almost impossible. I don't know, full day maybe. But using this tool, it uses a WinDebugger tool, which uses PyKDE to actually load WinDebugger process dump. So the idea is that whenever you take interPT dump, at the end of the session or in the middle, maybe you can take multiple dumps. You take process dump and you just save it somewhere. Later, you just combine this interPT trace with this process dump. And IPT analyzer will understand this WinDebugger process dump, right? So then it will just automatically extract the memory locations that are loaded inside the interPT. So very simple idea, and it saves a lot of time for you. So block analyzer, you just, the thing is that it's just reading caches, right? So it doesn't, these tools doesn't read interPT log directly, because it's kind of just flat files, and then you never know where is the locations that you are interested in. So before that, actually, you need to generate a cache file. So this is the tool, cache.py. So it will just enumerate any, it will just decode the full interPT log, and it will enumerate, because a lot of security researches are based upon the block start locations, function start, some jump, the location where jump is pointing to. So we just cache those locations. I can show you later, but usually those cache is from out of 1.4 gigabytes interPT log, 300 megabytes meaningful the packet data. The block cache is around 500 megabytes actually. Using this block cache, you can locate the locations that you are interested in very easily. So this one, find API call. So for example, you want to find, for example, kernel 32 crate file. So you pass it as an argument here. Then it will load the process dump. Then it will enumerate some modules, and it will resolve the symbol, and it will extract the exact memory address for kernel 32 crate file. Then it will just enumerate the blocks, right? Then we want to, CR3 is 0, but default is 0, but it don't, we are not actually just processing this right now, but address, based upon this address location, then you can actually find the actual PSB location that actually contains that crate file codes. right? So everything is processed by these PSB blocks. Then from this PSB block, we do further analysis, and we can actually enumerate each instructions that are calling this script file. So that is the idea. And here is one case study. Actually, I shared it through the blog post. This is one of the easiest and can be complicated example, because this is what is that? Office equation editor vulnerability from 2017. But there were a lot of variants found later, and Microsoft actually removed the binary. The thing is that this is Stack Overflow from very old legacy component from Office. But the thing is that the exploit technique is using actually returning some location. It's not ROP, but it's using some ROP-like technique. So from bug triage or vulnerability analysis point of view, it's not really easy to figure out what is happening there, right? Because you want some accurate information when that control flow changes. So that's why I chose this example. So I used WinIPT to just take the dump. This is the example you can just acquire from some public sources, actually. IPT tool is a WinIPT tool that is included in the Alex Ionescu's GitHub repository. You can just pass process ID and log file name. So, for example, I launched Office exploit, and it will actually launch equation editor as a decom object, right? Decom process. And I acquired the process ID and just pass it as an argument here. And output is EQ equation editor.pt, just name it. .pt is just process trace file. So it runs. The thing is that even though this tool is really cool, sometimes there might be some timing issues. There can be a lot of different issues. So maybe you might want to try multiple times. So, right? So sometimes it creates really awesome processor trace file that has full information. Sometimes, somehow, it misses something, right? It's not corrupt, but it misses some information that we need. We need it. So sometimes you get some partial dump. I don't know. I didn't root cause all these things, why it's happening. But you might want to try multiple times. If you look at the dump file and if you run pt dump or ptxed, you know that it's correct or not. So now you have the dump. You need to take process dump using proc dump, process explorer, then just take process dump from this process, equation editor.ex. Then you run IPT analyzer. Actually, the tool name is decode blocks. You just pass the process trace dump file. And this is a memory dump file. It will generate the cache file. So cache file will expedite whole analysis later. So if you run this command, I have some old Xeon machine at home. It has, I don't know, 32 core or something. So it's not super fast, it's not super slow, but it has a lot of cores, right? I ran it maybe 10 minutes, maybe 15 minutes. But the latest machines, if you have, I don't know, 16 cores, maximum maybe 10 minutes. Maybe if you have really slow machines, maybe, I don't know, maybe 30 minutes. But the block cache is just 500 megabytes anyway. So based upon that, like it's just running different Python processes using multi-processing component. So they are not just fully utilizing the CPUs, just 3%, because the Windows is just limiting the CPUs, is whatever. Then for this vulnerability analysis, because this is just one case study, how you can apply this Intel PT technology, right? So equation editor, if you did any vulnerability analysis or exploit analysis, you know that whenever the control flows changes, it's a bad sign. Right? We know that the vulnerability might be inside this equation editor, so we have some assumptions, and we want to know the memory address range for this module. So from the process dump, we know that it doesn't even use ASLR because it's a legacy component. So start and this range, we know that some code executed inside this address range did something and it made some malicious code control flow changes. So we want to dump any blocks, basic blocks between this memory address ranges, right? So using dump blocks tool, you just provide process PT file. You provide memory dump as you did before, and you provide the cache file generated beforehand, right? Then you give this memory range 40000 to the end address, so SNE. Then dump blocks will generate full log of basic blocks. So it will not generate full instructions. So it just shows the basic block changes. So it just utilizes the sync offset things, right? Block cache file contains block address and matching sync offset. So it just goes through this block cache file, and you know where is the PSP package that is matching that. So now you know that whenever something happens, this is just some casual investigation, but you can make some automation based upon these patterns of exploits later, actually. So that is something that I want to do as a next step for this tool. So this is more manual fashion. So your assumption is that the control flow change comes almost last phase to last instances of these basic blocks of this module. So this is the almost last part of these basic block changes. We know that maybe the return instruction here looks suspicious, right? If you don't find anything interesting from here, maybe you can try next blocks here. But this one might be interesting. Then you need to note the sync offset here. 2D236C is the actual offset from the process dump. And using this sync offset, actually you can dump the detailed instruction around this basic block. Then you might encounter some interesting instructions there, right? So using dump instructions tool, you just pass process trace memory dump, and the uppercase S argument, you pass sync offset, right? You got this sync offset from previous investigation, this sync offset, right? So you're dumping some instructions from almost the end of control flow changes from equation editor module itself, because if something exploited, it will come from equation editor. It will do some vulnerable code execution, then it will just jump to some shellcode or something. That is the assumption. So we just E is and what is that? PSV packet log sync offset. So we don't want to dump full things, right? So we just want to dump some range of this what is that? This PSV block. Now, if you just dump that last locations, it's a very small file. Then you can it will dump the instructions, actual single instructions, every single instructions. You can identify here, right? Instruction framework, equation editor frame, WinProg, some offsets, but maybe some buffer overflow happened just before here. So maybe you can do further investigation there. But the interesting point is here, right? So the end of this function call, it returns, but it returns again. Then it goes nowhere because this is a very legacy module. It doesn't use JIT or anything like that, but it just goes to some random memory location, the RWX memory location. If you investigate with the WinDebugger, you can see that it's RWX. Then it's running some code. That looks very suspicious. So we know that this is shellcode, right? So the return instructions actually this is more of, it's not RP, but this is some trampoline code that actually goes to the shellcode location. So this is that we now understand this exploit is using some return address trampolining to jumping into some shellcode. And we just pinpointed the actual vulnerable function, possibly, right? So probably this address, the function that has this address. So yeah, that is transcend non-image address. I mean, this is what I said already, right? So, and next stage shellcode, you can even use this as some shellcode analysis tool too, because it will log full image of shellcode. For this case, the shellcode is still there, and our process dump had all these instructions there too. And jump RAX, and we can even pinpoint where the next stage shellcode is actually running, the decoded shellcode and everything. So dump instruction shows, maybe you can use multiple dump instruction command to do further investigations how this shellcode is actually running. So conclusions. So this is not really about groundbreaking research, but it's more about introducing the Intel PTs for the general, so that they can use IPT analogy is just a casual tool that I wrote for my own purposes, right? But there is the concept, if you can decode this process dump within some reasonable time, and you can cache some information, some important information in a separate file, you can actually use it as a very strong tool for various purposes. Just I shared vulnerability analysis as an example, but you can, there is no limit actually. You can detect rootkits, you can detect, I don't know, some embedded threats, or maybe you can detect some persistency mechanism on your machine. Yeah, you just take 10 seconds of Intel PT log for your full system, and you can analyze there is any anomalies there. Maybe you can detect something interesting, right? Some code executions that are not supposed to happen, maybe happening there. So this is a very promising technology, and that is my conclusion. And that's it.
That's pretty cool stuff, actually. Thanks again for speaking about it. While we're waiting for some questions from the chat. By the way, can you imagine during all this time I thought your name was really Matt O. Can you hear me? Are you on mute?
Oh yeah. So yeah.
I really thought your name was Matt during all those years.
Yeah, Matt is my name. Yeah, for your convenience.
And a quick question, actually. Do you know a company called Tetran?
Yeah. They have very
Do they do something similar, or is it like something different?
Last time I checked, I think it's almost a year ago, they actually dissected what is it, the Windows kernel patch protection, right? So I think it's been a while, but I think they used emulation. But my memory might be correct. But I thought that it's really cool that they used some technology, but I don't think they used Intel PT. But you can use the Intel PT for that purposes too, right?
And is there an equivalent like for ARM, or is it just like specific to like?
Yeah, I know ARM has similar mechanism, but I didn't use it. I'm not really familiar with ARM. I'm more a Windows person, even though Windows runs on ARM too. But yeah, had it before Windows. The Intel, I think I remember. But you need more research.
Yeah. Same. I'm not very familiar with ARM. I just started to get into it. I was like, I feel like I'm missing out.
Yeah, usually ARM has some more advanced stuff before Intel CPU, right? Usually because they can move quickly with new features.
Yes, I've been doing a lot of cool stuff, but same thing. Like most of it would be like Linux based, so like I've always stayed away from it. Speaking of, there is Spender like from GRSec in the chat. He says thanks.
Yeah.
Yeah, that's pretty cool. So the tool is on GitHub. So you're using Alex library, right? The Win IPT underneath, which is using Windows driver underneath, right?
So the thing is that there are two phases. One is taking the dump. You can use any tools you want, right? There were three options that I gave you. One is the old Cisco Talos tool. If you really want to do some dumping from pre-RS6 machines, then there is one option. So after RS6, the tool says RS5, but after RS6, the tool is really working well. Win IPT, you can use Win IPT. It works really well. Just make sure you take multiple dumps and just compare those dumps, because sometimes it fails because it's not the tool itself, it's IPT.sys or maybe timing issues, right? The ultimate option is using Intel debugger extension. Okay. The only problem is you need a physical debugging interface, and you need to invest $20 for the debugging cable. And making USB debugging, kernel debugging, working on your systems are really challenging. For someone, it takes days.
Yeah. And
Once it works,
is it using like a serial port or something, or?
Excuse me, what was that?
Is it using a serial port for like the physical debugging, or?
USB 3.0.
Oh, okay.
So yeah, it's connecting to the remote machine. So I didn't dig deep, but Intel extension is sending some package. I don't know there is any open specification about that, but you can easily debug or reverse engineer this Intel PT extension to figure out what kind of package it is sending to the remote machine to enable this Intel PT logs. It will be interesting too. Yeah. Then you don't need to potentially use Win debugger for that purpose, right? You can just build your own Python library that is sending same package sequences to the remote debugging machines to enable those features, I guess.
But there is an extension for Windows DBG.
So. Yeah. Okay, so you just need a Win debugger, Intel extension. You can just download it from Intel website. It's free. You just install it. But it has a little bit of a glitch. It has some glitches. You need to patch the binary to circumvent something. I can share later.
Oh, you need to actually like patch the actual extension.
Yeah, but it's not really core function. But it checks something. But somebody asked that question 2 years ago. Nobody answered. And if you Google that problem, there is only one entry from the Google search results. And someone actually asked on the forum on the Intel. Nobody answered for 2 years. Oh. And I figured out it is some bug inside the Intel driver. But it's not the critical bug, but it's just some accessory check on the driver. Then you just patch it out and everything works perfectly. So I can share that later too.
I see. Yeah, that's pretty. And is it because like Intel PT is not like widely used since it had been released, or Or come it was like leftover? Because from what I remember, when it got released, it was like something quite powerful for tracing. People were like, it's like really cool. Like Richard Johnson was, I remember, was like really excited about it.
I have no idea, actually. I have no idea why. Maybe someone is already using it a lot, right? But Intel PT, so I'm looking into different technologies, right? I used TTD at Microsoft, even before it was public. I thought it was cool. Intel PT can be more powerful, right? But it doesn't save the context. That is a limitation. So it has a limitation, right? It doesn't save the CPU context. It doesn't save register values. Sometimes you can potentially lose instruction bytes if it is JIT or shellcode. So those things can limit the usage, but still, I think Intel PT is really powerful. And using these tool bases, then you can make it more, if you make it more easily accessible, then I think you can find a lot of application of this technology. I remember someone talked about UEFI tracing using Intel PT. Those things, right? Those things are really cool. So
yeah, especially for that would be quite cool actually for UEFI, because it's probably not as complex as Office. And I mean, if you trace like because like how big did you say like the cache file is now, or like a few gigabytes?
Cache file for what?
Office? The block cache file when you're like doing
for mine, I can share, I don't know, I can share my screen, right?
Yeah, you're still sharing it,
yeah, you can see that.
Yeah,
I can hide so this is full trace actually for IPT. There were some failures, right? So PT file, this is the case, right? The PT file is just 11 megabytes. It doesn't make sense somehow. So normal PT file should be like this, 1.4 gigabytes. The other thing is that you remember that I talked about all this compressing, all these things, right?
Yeah.
But most of them are just 0.
Oh wow!
So so they used a lot of so because it's just a ring buffer, right? So but it makes sense. But
you could still compress it like before, right? I mean, I don't know.
Yeah, so if you compress, and still it's just 3 megabytes. So look at this, right? So the PT file is not really big. So you just record full trace. It only takes 3 megabytes of your disk space for just Intel PT file. You need to take the process dump, right? Process dump file. I don't know where I saved it. Oh yeah, process
and
dump.
At which point are you taking the process dump? Like after you want to analyze something, or before to compare?
You can do both, right? You can do both, and you can compare that later. But for this case, you can just take you can actually attach debugger to equation editor and just hold it before it exits. Or you can use proc dump to take dump whenever some processes exit. So there are a lot of different techniques, right? I took it when the process exits. So it's a 1.6 gigabytes, but you just compress it, just 44 megabytes. So 2 information sources, you just generate a block cache file. Then block cache is 500 megabytes. It's just, I didn't do any optimization. This is just Python, the structure, serialization structure. I don't remember the name, right? So it's just a loose file. I didn't do any compression, right? If you compress it, if you just split it, it's just 100 megabytes or something, right? Then using this information, you can do some analysis here. For example, I can share this. For example, this one. Find the API calls, then you just pass these things. For example, I was just suspicious maybe it will be executing shall execute, right? Because it's just showing some dialog boxes saying it failed to run something, or you can just search for these API calls, or maybe it's dropping some files. I want 3 cases. So find the API calls, output for shellcode execute. Yeah, you can get actual location. There's just one instance, right? So it's very exciting that you know that, oh, this sync offset has this information. Maybe you can trace back from this location where this shellcode execution is coming, right? Even for URL download, I don't know, it was not there. Create file. You wanna enumerate every instances where the file is created, files are created, and you can dump. The only problem is that you don't know what is the file name, because file name is just short-lived and just goes away.
Yeah.
Right? So that is the limitation, but still it is very powerful because it is full instruction dogs. Nothing is missing.
And it's tracking like each instruction, not only like the branch jumps, right?
Yeah, it's just expanding, right? So
okay.
Process trace dump, original dump only records meaningful control flow changes. So that's why it's really small. Combining with real images, process dump in this case, you can reconstruct full instructions for basic block changes, right?
Okay.
So that process, the converting process, takes long time. So this approach is like more like, let's look at the basic blocks first, because if you want to decode full instructions, it will take forever. But the meaningful changes, they usually happens by basic blocks, right?
Yeah.
You only caches basic block locations, that is 500 megabytes. So based upon those basic block locations, now I want to know where the shellcode execute happened. Then from the process memory dump, we know the exact location, right? Because it's there, right? So we just retrieve that memory address and searches for basic blocks, whether that memory location matches any cache locations. And that cache location has information to the actual PSB block inside IntelPT file, right? Now, from the IntelPT file, now we extract the actual instructions. So it's more of a step-by-step approach from this full IntelPT file to basic blocks, functions. Then we go deep into the actual instruction levels. In that way, you don't need to dump full instructions, right? And you don't need to dealing with this huge instruction files. You just focus on the basic blocks.
Okay. And actually, I'm just checking your blog post now. There's a comment you didn't answer. I'm gonna read it for you. There is an MSR register, debug.ctl MSR, that can be used to track branch jumps. Is there a difference between this and IntelPT? Is IntelPT better?
Yeah. So the truth is that I'm not really expert in Intel CPU architecture. Right? There are better guys out there. But from my memory, actually from the reverse engineering community, I remember it was, I don't know, 10 years ago, 15 years ago. I think it was Pedram Amini. I remember that he tried to use those branch records to save something. But
so it's pretty old, though? That MSR is
really
pretty
old, I guess. There might be some technology in between the branch recording and something inside, something between. But now we have this IntelPT, and I don't know, maybe 90% of machines that you have right now might have these features enabled already. So you don't need any new investment if you have one machine. So the approach that I'm doing, because you need to run some malicious code on your system, right? So usually what I do is just use USB stick. You just install Windows image. So you can just search some information on internet. You can find how you can install Windows on your USB SSD card or something like that. It's, I don't know, $30. You just buy them, just install Windows to go. There are public tools available, not from Microsoft. From Microsoft, you need a special USB thumb drive, right? A very expensive one. I don't know, I remember maybe $100 or something, but there are some public tools that convert your Windows image to USB thumb drive image, right? Then you just boot from your USB thumb drive. Now, potentially maybe malware can damage your hard drive, but there are limited chances, right? So you just take chance and you can just run, you can just run from the USB thumb drive, you just run whatever. If you are researching malware, just malwares, I don't know, anything there, you take the information, you collect all those information, you can just reuse your laptop after rebooting as your normal operating system. So you don't need any additional investment for this research, because people think that, oh, for this, because this is using hardware features, maybe I want to buy new laptops, maybe $1,000, $500. You don't need new investment. Just using your normal machines. If you don't run really super malicious stuff, I don't think it will install something to your hardware. So if it's reasonable, then you can just use it. Then if you are really serious, then you can just buy some machine, $500 machines or $1,000 machines, to run these things as just malicious box that you can run these things and collect things, analyze. There are a lot of possibilities, and I think there might be some security product you can build up on this technology too.
Yeah, I mean, even for sandboxing, that you would get something like much better than what you have now, I guess.
Yeah, the only problem is that you can't take out those dynamic memory contents. They are just
I see. Cool. Actually, one question from the chat: is it possible to get extra information about these extracted addresses? For instance, some vOPCDE protection rights, flags, and so on.
Can you repeat the question? I don't understand the question very well.
Oh, no worries. Is it possible to get some extra information about those extracted addresses? For instance,
no, it's just address. It's just,
okay.
There are, you know, that there are, whether it is from CR0 or CR3, so you know that whether it's a kernel instructions or just user instructions. You can know that there are a lot of packages that indicate whether this is coming from the privilege page or not. So you will know that it's kernel instructions or not.
Oh, because you have the control register, since you have the context also?
No, there are separate packages showing that, oh, from now on, it's executing some userland instructions.
Oh, I see what you mean. Okay. Okay, interesting.
There are a bunch of different packages out there.
So you not get the actual Windows structure, but you get like the CPU information, which would contain like more or less something like more or less similar.
Yeah, I can. Let me see. I can show you. Yeah, this is the ptdump output. ptdump is the tool from libIPT. So if you run ptdump like this, just ptdump is just from libIPT, right? You just compile it and just run pt. I removed the MTC. This is timing information. Right? Pad is just padding. So this is ironical because they wanted to save the whatever this memory and trace log. They are go extreme as like a logging jump and non-jump as just 1 bit, and they leave a lot of padding bytes, and they just waste huge space. So if you don't remove them, the ptdump file will be huge. So if I remove them, 1.4 gigabytes of dump is just mere 169 megabytes or something. So you can read it. PSB starts. This is, I think, timing information, but it's not really important for us. Those are for some performance tuning purposes or whatever those other purposes than security research, I guess. TMA, I guess, timing, CBR, I don't know, PSB, and so this is a PSB packet. Timing, a lot of timing informations, right? So mode exec, I don't remember what this is, but TPG, I remember there was some CR3, CR0 informations here. But yeah, I forgot a lot of things. TSX, exec. Yeah, I can find it here, but
Yeah, it's okay. Don't worry.
yeah. There is a instruction that shows whether this is from kernel or userland. Yeah, then
That's
from
cool.
there you figure out. Yeah, that is extra information. And as new CPUs are coming out, probably they're adding new packet formats, possibly. Yeah.
That's cool.
Yeah.
Well, there is no more questions from the chat. Thanks again for joining us and for your excellent presentation. Don't forget to send me the slides. I see.
Yeah.
Can you even export them? Like I see you're like using like localhost for your presentation. Oh no, it's in HTML. Okay, that makes sense.
Oh, this one? Yeah, I can export as a PDF. This is
awesome.
Yes. So I will share it later, maybe today. And thank you for inviting me to do this cool conference. I really like it.
Yeah, no worries. Thanks again for speaking and joining us. Well, I guess have a good day.
Yeah, you too. Bye.
Thank you.